Imagine you walking down a dirt road and you pass in front of a farm of a rich man. The rich man rests at the gate and invites you for a challenge. He says that if you can find his needle in his haystack, he'll give you $10 million or euros, since you are here. Um, there are a lot of ways to approach this challenge. You might stop losing your time right away and start looking for it. After all, you can spend 5 years looking for it, but after you find it, you don't have to work for the rest of your life. Well, finding life in other planets is a similar task, but it's important we understand where life cannot be found.
Hi, my name is Arthur. I'm a computer developer and I have a thing for astronomy since ever. I work at USE, the first insurtech of Brazil, and it was born as a startup to change the insurance market in the country. And he is Lucas. He's a student of astronomy and physics at the University of São Paulo, and he's currently working with the structure and the dynamics of the galactical spiral arms through the study of open clusters. Not computer clusters, just star clusters. And what we brought here today is a glimpse into his scientific initiation project. Well, we don't have all the answers. I certainly don't have them. But if you want to contact us, feel free to write to us through our Twitter accounts. When we try to understand the universe, we inevitably stumble across a question that's really hard to answer. Who are we? For many centuries, we put a lot of importance on humankind, but at the end, we are just little grains of sand in a tiny little planet in the corner of one of so many galaxies. Even the universe may not be unique. We don't know that for sure. There is this lesson on public speaking that says we should build the audience's morale. Sorry about that, but we are basically unimportant. But don't hate us, because our point is we are a living miracle. Our existence is statistically impossible, and there is no evidence that there is anything slightly like us out there. Nonetheless, we are putting all our efforts to find it, and this is the purpose of this project. Let's find other grains of sand. But what are we looking for exactly?
Well, the needle is developed life. We're talking about intelligent life, of sentient beings that are capable of communicating back. We get asked a lot, why do we look for life that resembles us? For example, what if life out there doesn't need water to develop?
Well, that's a fair question. What if life out there does not? What if life out there is immune to our senses, for example, is invisible to all our equipments? Well, it may be the case, but let's be honest here. What's the difference for us from such a life and a life that does not exist?
And we have the haystack, and the haystack is our galaxy, the Milky Way. It is a haystack, and it is huge. It has 100,000 light years from one end to the other. That means that a light beam, which is traveling at the speed of light, would take 100,000 years to get from one end to the other. Our estimate is that it contains 250 billion stars, giving or taking 150 billion.
If you take an optimistic guess, like 400 billion stars, we are talking roughly of 10 stars for each grain of sand on Earth, according to some estimates. That's a huge number. And if we Google now where we are in the galaxy, you are probably going to find an image mostly like this, with a yellow dot somewhere saying you are here. Looking at this image, we have the deceiving impression that we are closely surrounded by stars. That's wrong. The closest star from our sun is Proxima Centauri, and it is more than 4 light years away from us. So these stars are really far away from one another.
That gives us hundreds of billions of planets that can host life. So, can we narrow down our search? Well, first, we need to understand the conditions that make the presence of developed life as we know it possible. And these are the conditions you might have already heard of. These are the basic conditions for life. The first one would be a stable source of energy, like our sun is to Earth. It's better if it's not a very wild star with insane variations in brightness and a lot of plasma ejections from the star. And it needs to be stable because we need the distance from what we call the habitable zone to the star to be constant. The habitable zone is where water can be easily found in the liquid state. If it's too close to the star, it's going to be too hot and water is going to evaporate. And if it's too far, water is going to be found as ice because it's too cold. And as you might already be thinking, the other thing we need is water. We all know the importance of liquid water for life here on Earth, but we might not think about the importance of water vapor. Water vapor is a key compound of the greenhouse effect. And remember, the greenhouse effect is a natural process that warms the surface of a planet, allowing the temperature to be constant even during the night. The next thing we need is what we call a benign environment. These are things like a rocky planet, so we can hold water, and the presence of a magnetic field, so it can protect the planet from plasma ejections from the star, and appropriate composition of the atmosphere, and so on. But there are also some more complex conditions for life. These are the ones that make finding developed life as we know it a little more unlikely. It turns out that the greenhouse effect produced by water vapor is not that stable. So we need a continuous geological activity that can emit and absorb gases. These are things like volcanoes and erosions, so it can maintain an equilibrium with the temperature even if it gets too hot or too cold. The next thing is very intuitive. We need a star that lasts longer than the time required for life to develop. Earth is about 4.5 billion years old, so it's natural to look for stars that have at least that age. So very young stars are out of the game. And the next thing is not very mentioned, but will be the one we'll be talking about in this talk today, which is the distance from the galactic arms. But first, let's clarify a couple of things. What are the arms? What's going on in there? Well, we live in a galaxy, in a spiral galaxy called the Milky Way. And a spiral galaxy is a galaxy that has the shape of a disk, and these spiral patterns, that's what we call them. You can think of the arms as waves propagating on the galactic disk. And you can think of it also as a traffic jam, but it's just a region of higher density, but instead of the cars, we have the stars. And as you know, in a traffic jam, the cars that make up the higher density part is not always the same. They're always being replaced. And the same thing happens here. The stars that make up the arms are not always the same. But that difference in density is not that expressive. And so, how come we see those regions so highlighted from far away? What we see is that the galaxy is full of gas, and the gravitational disturbances created in the arms allow the gas to collapse. And that gas, when it collapses, it forms new stars. And as you might think, the bigger the star is, the more massive the star is, the brighter it will be. But it turns out that the bigger the star is, the less it will live. And that is because a big star needs way more fuel to counteract its gravitational weight than a small star does. And since this is a region of star formation, and there are a lot of bright stars, and those stars don't have time to leave the arms before they die, that's why we see those regions so distinguished. But that leads us to the danger that spiral arms offer, which is the death of a high-mass star. When a high-mass star comes to the end of its life, a very energetic phenomenon is about to happen. The star no longer has a fuel inside it to counteract the gravitational weight of itself, so it collapses. And some elements that make up the star, that make up the nuclei of the star, fuse into one another. And that creates a huge amount of energy and of radiation. That's what we call a supernova. The presence of a supernova nearby can entirely destroy our ozone layer and ionize atoms in our atmosphere forming harmful compounds for life, and even damaging phytoplanktons and reefs, entirely destabilizing our ecosystem. And not to mention the gravitational impacts it could produce, it could maybe take Earth away from its comfortable orbit. So, if you want to find life, we better start with a star that hasn't crossed an arm in a long, long time. But is that even possible? Well, what is observed is that the stars and the arms orbit the galaxy in a different manner. This is what we call a rotation curve. It shows how the speed of the objects change depending on the distance from the galactic center. The disk is represented by this dashed line here. And as we can see, the disk orbits the galaxy like a solid body. It's not a solid body, but it orbits like one. That means that the further it is from the center, the faster it's going to travel. However, the stars, they're represented by this continuous line and the dots, they have a speed that is nearly constant no matter what the distance from the center is. And that has to do with dark matter, but that's a whole other subject. And as we can see, there's this one region where those two velocities are the same. That means that both the stars and the disk have the same speed if they have that distance from the center. If they have the same distance from the center and the same velocity, they orbit together. And that's what we call co-rotation. They're rotating together. If we have a star that is in the co-rotation region and it already has a distance from the arm, since they have the same speed, they're never going to meet each other. On the other hand, if we have a star that is closer to the center, in this area here, its velocity is going to be greater than the one of the disk. It's going to travel faster than the disk, and it's going to cross an arm, which is dangerous. And on the other hand, we would have a star that is further from the center, and its speed is going to be slower than the one of the arms. And that's going to cause the arms to cross the star, which is equally dangerous. So that's our safe spot. Anywhere else is much less likely to find life.
We are talking of finding life out there, but how can we actually do it? We are going to see some super helpful tools, but let's start right away with the most polemical choice.
The integration method.
What? Now, we disagree on that point, but I am in control right now, so we are talking about the programming language. We chose Python. Why? And here comes a wake-up call for all developers out there. We tend to choose the programming language based on the language we are more acquainted with. Then we come up with rationalizations, trying to convince ourselves that our decision was based on logical arguments, but it's not exactly true. At the end of the day, it's not always the language we worship the most that gets the job done. So we have to be humble and honest and choose the right tool for the right job. We didn't choose Python because we are good at it. In fact, we know so little of Python that sometimes we felt like children groping the musty walls of a dark underground corridor, which is usually the case when you work with astronomy. But if you know how to code, you can find your way through the uncertainties of a new language. Google is your friend. Stack Overflow is your dungeon master. Use them wisely. We chose Python because it has amazing scientific libraries like Matplotlib, SciPy, galpy, and so many others. Then we had a huge problem to solve. We are talking of things that are light years away from us. Things that can be hundreds of thousands of times bigger than Earth. And while it may work well in the minds of the astronomers, for us, mere mortals, it's really hard to see what's going on. So we needed to find a tool that allows us to have a visual representation of the work in progress. And for that, we chose Jupyter Notebooks. It has a neat web interface where we can write text that will later on work as a documentation, but we can also write Python code in there and have the result nearly in real time. We are going to see it in action in a moment. And last but not least, most scientific research is built on top of a huge data set. We need data. We are talking of checking the stars to know which one has a good chance of having planets with developed life as we know it. So it stands to reason that we have to know the stars first, right? And luckily for us, we don't have to do all the work ourselves. People a lot smarter than us, with so much more resource, have already done that. The ESA, European Space Agency, is mapping the galaxy, and the result is Gaia Catalog, which is the framework of our work. It's free, it's open, it's on the web for anyone who wants to use it. I think it's time to take a break from the slides and get our hands dirty a little bit. For those who does not know it, let me introduce you to Jupyter Notebooks. It looks a lot like a text editor. As you can see, we have already written lots of information in there. This notebook is in my GitHub, so if you want to read it later in your own time, my GitHub is Artur CP. This repository is called Co-Rotation Notebook. There is also another Co-Rotation notebook repository there with a crawler we are going to see in a moment, so you can take a look later at things. But I think that the best approach here is to start by the end. So let's take a look at the result of this notebook. You're looking at an animation of our galaxy spinning around with its arms. Try to do not look at the black dots as stars. As he said, the stars are not always in the same place. It's just the high density area. And the stars are out of scale, okay? These colorful circles. The first impression we have here is that everything moves together, which is not true. The movement of the stars can be really chaotic. So we draw those three stars, and they represent the three possible outcomes of the speed of a star in comparison with the speed of the arms of the galaxy. Let's look first at the blue star. Its movement is slower than the arms. So at any given moment, the arm is going to cross it, like right now. And as he said, the arms are very dangerous zones. They are full of gas, they are full of heat, they are full of explosions. So any life that orbits that star is probably doomed. Then we have this red star, and it has the opposite problem. It moves faster than the arms. It will not be crossed by the arm, but it will cross an arm, and its destiny is probably going to be the same. And finally, we have this purple star. It's moving at the same speed of the arms. It's not 100% precise, it should not be touching the arms, but I think it's good enough to show our point. It is in what we call a co-rotation. It's never going to be crossed an arm or cross an arm, and we want to be around that star because it's not in our agenda to be blown up by a supernova. Now that you are all hypnotized, let me show you the best code of your life. The best code of your life. This is a very simple code. It will serve as a warm-up for what comes next. There are some key concepts here that are going to be useful to understand the next notebook where we are finally integrating the orbit of a star. It all starts with this call to the matplotlib line. We are just telling Jupyter to plot charts here. Then we imported a few libraries. The gist of it is that we are importing pyplot and animation from matplotlib and the image from scipy, then numpy, and image.io. And we started the code by reading this galaxy-wide PNG file into this img variable. This is the image of the galaxy we were seeing a few seconds before. Then we needed to create a figure to hold the entire animation. So we did that, and we configured it by setting its DPIs and its size in inches. We have also created an X and Y axis, a 20 by 20 axis. And then we want to draw three circles, three stars. To draw the stars, we use the circles, and the circle accepts a few parameters. The first one is the X and Y position. It does not matter very much right now because we are going to change it later, so never mind it. But then we have useful attributes like the radius of the star and its color. Let's skip the next two methods because the next executable line of code is this call to the animate function. It accepts a few parameters like the figure to animate, an animate method, an init method, and other things like the number of frames, interval between frames, and so on. You can find the full list in the documentation. After that, we are just hiding the axis, saving the result in an MP4 file, and plotting something here. As you can see, Jupyter ignored the animation and plotted a static image. But before we tackle that, let's get back to the methods we skipped. There is nothing special about the init method. It's going to be called once, and only once before the animation starts. We are just adding the stars to the axis. But there is something very special about the animate method. It's going to be called once for each frame in the animation. It's here that we are going to move the stars bit by bit, one tiny bit for each frame in the animation. So if you are looking here at three main blocks of code, they are doing basically the same thing for each star. And we are just changing the X and Y position of the stars. So all of them starts at 10, 10. It's a random number. We picked 10, 10. It could be anything else. And that's because 10, 10 is the center of the orbit of the stars. Then we have here plus 8. That's multiplying sine or cosine of something. And we all know that sine and cosine varies from -1 to 1. So what we have here is basically from 10 minus 8 to 10 plus 8. We can safely say that 8 in this case is the radius of our orbit. And the same thing for the others. This one has 2.5 of radius, this one has 4. Why are we using sine and cosine? I know it's not very intuitive at first, especially if you don't use this in your daily routine, but those mathematical functions force the star to move in a circular path. If you have time later, go to my GitHub. We added a very cool animated GIF here that explains how this process works. So the thing we are using on sine and cosine is I. I is the number of the frame. So every time the animate method is called, we receive the number of the frame through this parameter. We are multiplying it by different numbers just to change the speed of the movement. So we can have the blue star moving slower, the red star moving faster, and so on. Now that we moved the stars, all that's left is to rotate the galaxy. We try to use an image, an animated GIF as a background, but as you saw here, Jupyter ignored the animation. It didn't let us do that. So we decided to rotate the galaxy ourselves, just like we have done with the stars. Our first attempt was with a transparent background image. Didn't work very well because it left a trail behind we could not erase. So we added white background. It worked better, but after every movement, the animation was resized to fit the figure. So we had the weird impression that the galaxy was shrinking. After struggling 1 hour with this problem, we finally went to the documentation and we found this reshape false here. It worked like a charm, so here goes an extra tip for today. Go first to the documentation. And thanks to that, we can now see what's the purpose of the project and where we are in the process.
As we've seen, the Gaia catalog has already mapped 1 billion stars. And that data is free, it's precise, and it's out there for everyone who wants to use it. It's hard to imagine recent astronomy without a huge amount of data. And with that comes the necessity of using coding to process all that information. But first, we need to get data from the catalog. This is an extract of the Gaia catalog. It gives us things in equatorial coordinate system, which is handy when we want to find things located here on Earth. It gives us things like what is the distance from the equator on the sky and so on. But for our purpose, it's not the best idea. So we're using another version of the same extract of the catalog, but these are in the galactic coordinate system, which is much easier to deal with dealing with our project.
Looking at that, it's really hard to understand what is what. It's hard even to understand that those things are columns. So if you go to the documentation provided by Gaia, you can learn what each column means and also how to extract the data from each line. So you can see that the first 18 characters goes to the name of the cluster, the next 8 goes to the longitude, and so on. And we also have this label column here. That's because scientists use labels to represent things. And so here we have the official labels for each of one of the columns. Okay, but working manually with the catalog is not a good idea. Not only because it has too much data, but as you can see here, we have some gaps.
This is missing information. This could be like it doesn't have the radial component of the velocity of that star. And as we're going to see afterwards, for an orbit integration, we need some information like the position and velocity. And for example, if we don't have the radial components of velocity, it's not going to be able to integrate the orbit, and we can't study the star that way.
Instead of working manually with that, we created a very simple Python crawler. There is nothing special about the code, so we are going to see it very briefly. This crawler does only two things. It reads data from the source, and the source can be either the web or a file. We did that because we were not sure if we would have internet connection at the time of the presentation, or even if the catalog was going to be up and running. So it works both ways. It reads data from the source, it prints the results. If you look at the print results method, it looks to have lots of lines of code, but on a closer look, we can see that most of the lines are just formatting the result in a nicely friendly way to be shown in the terminal. So let me show you it working. The font size is small, but I think it gives us an idea. It looks like a table. We are showing only the columns that are relevant for us. There are no more missing gaps. So each line here is ready to be picked. So we can work with that. The secret of the crawler actually lies in the cluster class. We pasted the documentation here to make our life easier. And this class has a class method called fromLine. It receives one line of the catalog. One line can be simply like that. And it knows how to extract data. So it will instantiate a cluster and add the value to the attribute. So the first characters goes to the name, the next 8 goes to the longitude, and so on, according to the documentation. We have also created one method for each attribute using the labels, so anyone can use this project in a more scientific way. And here at the bottom, we have a very clever method called valid. And it's here that we added the rules that we needed to fulfill in order to integrate the orbit of a star. So he said we needed the radial velocity. It is here, it must be present. There are some other rules that must be fulfilled. Now we can go back to the print results and see it's quite simple. We are navigating through the catalog line by line. And for each line, we instantiate a cluster with data. And if it's valid, we print it to the terminal.
Okay, this is so good. But the only thing gives us is the position and the velocity that the star has right now. Even if we pick those that are in rotation now, how can we know it has always traveled the safe path? Well, for that, we use Python to go back in time and analyze its behavior throughout its existence. And that's what we call an orbit integration. It's the simulation of the trajectory of a celestial body, knowing its current parameters and the physics they are applying in such context.
We have here another notebook. We are finally going to integrate the orbit of a star. And again, to integrate the orbit is to make the object to go back in time. We are from the current moment to its birth, so we can know if it has always been in rotation. It's also in my GitHub. You can take a look later with more time. And it starts basically in the same way as the other notebook. We have a call to the matplotlib line, and we imported a few libraries. But this time we have a highlight here. The life of the party is galpy. The first version of this project was done using IDL, which is another programming language, and we had hundreds of lines of code just to make the integration. You're going to see that galpy allows us to do that using one single command. So we start by choosing a potential. If you remember this chart that Lucas showed to you, we have this dashed line which represents the speed of the arms of the galaxy in comparison with the distance from the center of the galaxy. The change is linear, so we have this dashed inclined line. And we also have that other line that represents the speed of the stars. So the stars get really fast, really quickly, but then it stabilizes. It's almost an horizontal line. And the potential is going to serve as a guideline. It will represent the line of the speed of the stars,
which shows the logarithmic halo potential. It is the simplest one, and it showed us some good results to what we wanted to achieve.
This is the line of the logarithmic halo potential, so it's basically an horizontal line. There are some other potentials you can choose from. We added some examples here, but there is a huge list you can find on the documentation. Now it's finally time to pick an object from the catalog. We picked one with 10 billion years of existence. So we created this TS variable. It works just like an array. It starts at 0, it ends at 10, which is the age, and then we divided this interval in 1,000 small pieces whose units are giga years. This works exactly like the frames in the other animation, the other notebook. So each frame is where we are going to move the star one time bit at a time. Then in order to integrate the orbit of a star, we need to create an orbit. We created two, actually, one for an object that is in rotation and one that's not, so you can see the difference. And this orbit has a few parameters. The most important one is this very weird Vx, Vv.
This is where the input from the catalog should be. This asks for the relative parameters, the relative conditions of that orbit. And it asks things like the distance from the galactic center, the radial components of velocity, the transverse components of the velocity, and so on. And I say it's relative because we also need to set the information we have for our sun. So here I'm saying that our sun is 8 kiloparsecs away from the center of the galaxy, and it orbits with a speed of 230 kilometers per second. So the first orbit would have 95% of the radius and 4% of the radial components of that velocity, and the other one will have 110%, and so on.
So it's time to let galpy do its dark magic. We are calling the integrate method over the orbit, and we are passing the TS variable, the potential, and a method. We are not going to dwell on this method right now. It's a very broad subject, but just for you to know, we are using the RK6C, which stands for the Runge-Kutta method. And to plot things is boring, so we are going to animate things a little bit. This is the orbit of a star that is in rotation.
Oh.
Now let's take a look at the orbit that's not in rotation, which is a lot cooler.
Oh. As we can see, the orbit that isn't in rotation had a huge variation in brightness. It went as close to the center as 2.7 kiloparsecs and as far as 8 or 9 kiloparsecs. On the other hand, the star that is in co-rotation had a little variation. It went from 7.6 to almost 9.2, which is within the co-rotation region. So as we can see, the one that was not in co-rotation got too close to the center, and that means that its speed was greater than the one of the arms. And that means that it almost definitely crossed an arm, and any life that was hanging out there, that was just chilling, is probably dead by now. So, what are the consequences to what we've done? Well, this is an illustration of our galaxy. And this was the search area for life that we had before. We wouldn't make in time for the build stuff party tonight or tomorrow night if we had to check every single star in their region. But if you only choose the stars that are in co-rotation and have been in co-rotation for a long time, we're left with a much smaller area, which is very handy when you want things to be found before the world ends. And due to the amount of dust and gas in the center of the galaxy, only one region would be reachable, would be accessible for us to see. So this is the actual search area for life. But what about us? Are we doomed? Should we be worried about a galactic motivated mass extinction event? Well, no. This is where we live, in a very cozy spot in a banana-shaped co-rotation region. So, spare not. We're safe. At least, for now. Orbits are a very fragile thing, and we never know when something's going to happen that's going to change everything we observe now. But that is a very unlikely event, and it won't happen anytime soon. So now, we're a little bit closer to finding out if the predictions made by science fiction, all those alien friends we've had since a child, are somehow similar to what's out there. And if so, we hope that some are more friendly than others we know about.
Let's all pay attention to the next slide. That's all we had about global warming. Thank you very much.
Let's see if we have some questions here. We don't know how to use it. We don't have any? Oh, it's redirecting.
Something's happening here.
Does anyone have a question? They want to raise their hands? I don't know. It's not showing here. Could be, yes.
It's a bit astronomical, but the arms of the galaxy, have they been forever?
Yes. Our galaxy is about 13 billion years old, which is about the age of the universe. And we think that the elliptical galaxies there is the other type of galaxy. They're just a bunch of stars in an elliptical shape. That they are the earlier type of galaxies, and any gravitational disturbances it could produce, it would make the galaxy to flatten out, and another gravitational disturbances would create the disk. It's very easy to disturb a galaxy, and the consequence to that disturbances is the disk. So the arms of our galaxy have been here for the longest time ever. Anyone else? Yes. What is in the center of the galaxy? As in other galaxies, there is a supermassive black hole. We can't see the black hole by its definition. Light cannot escape the black hole, so you cannot see it. But we presume that by analyzing the orbits in the objects that are really close to the center and making the calculations, we discover that there is a object with a huge mass, and astronomical mass per se. And it's a supermassive black hole, and we have extended that theory to almost every galaxy in the universe. They have a supermassive black hole in the middle. Yes, you had a question?
You mentioned you were talking about galaxy arms and stars, but what do you mean by galaxy arms?
Yes. The star, we can think it's homogeneous. We have a flat disk with gas, dust, and stars. However, the arms are just like a wave propagating. It's made of the same stuff, but it has a little bit more. It's just a region of higher density. Imagine you're driving a car and you stop at the red light. There's a higher density of cars. All the road is made by cars, but in that region you have more cars. And also, the stars that are in the disk are more bright, so it's highlighted. It's different from the other parts, and that's because there are bright stars, and it's much less likely to find bright stars in other regions because they die too soon. And since they're born there and they don't have time to leave it, they stay there, and those regions stay highlighted from far away. But it's made of star, dust, and gas, just like any other point of the galaxy.
Stars can be either on the galaxy arm or just separate.
Yes. Yes. It's for us as we study it. We understand that all the stars are made in the arms. They are born there, but they leave somehow at some point, and they can come back or not. But they're all born there, and they take their separate paths. You had a question? The Gaia catalog? Well, it has 1 billion stars. It is huge. And it's on its second data release. It's going to have another one. So we're expecting more data. So that would be about it. 1 billion stars for this one. But that extract that I showed you is not actually the entire Gaia catalog. It's just an extract that selects the open clusters, which are clusters of stars that are born right now because they're born together of the same cloud, and then they go separate ways. But right now they would be close apart. Those are open clusters, and that extract I think had only 700 stars. I think because it's hard to understand what is an open cluster or not, because they need to have some characteristics that are intrinsic to the open clusters.
About the processing of data, we didn't process everything. This is just an extract of an ongoing project, so we didn't do a full processing of the data. But it's probably going to need something really powerful to do that.
Mm-hmm. Anyone else? Nothing?
Okay, if you remember something you want to ask later, we are going to be around, so just talk to
Yes.
us. We'd like to talk to you. So
Yes.
thank you.
Thank you.